Hello everyone, this is Aidan for Fluid Mechanics 101, and today I'm going to be talking to you about the K-omega SST Turbulence Model. Starting with an overview of what I'm going to talk to you about today, I'm going to be talking about how is the K-omega SST model different to the K-epsilon and K-omega models. I'm going to look at what is the blending function, F1, and then also going to talk about what's the difference between the K-omega BST model and the K-omega SST models. And I'm going to finish off by looking at viscosity limiters and what is a viscosity limiter. So to start out with the background for the K-omega SST model, it's important to remember that historically the K-epsilon and K-omega models were developed first, and the K-omega SST model was developed as an improvement on these original models. Now, the K-epsilon model was developed first, and it was found that the damping functions that are necessary in the K-epsilon model become unreliable when applied to a variety of flows that are different to the original flows that were used for their calibration. And so the K-omega model was developed in response to this to give better near-wall behavior that's less sensitive and doesn't require near-wall damping functions. It was then found after the K-omega model was proposed that the solution values for the K-omega model were actually sensitive to the free stream values of turbulence applied at the inlet to these computations. And it should be remembered that this would typically be an external aerodynamics application, say flow over a wing or an aerofoil, and we're finding that the solution, the lift and drag, was sensitive to the values of turbulence intensity, length scale that were applied at the inlet to these computations. And for both the K-epsilon and the K-omega models, it was found that the flow wasn't separating correctly from the smooth surface of the body when compared with experimental measurements, and this is primarily because the wall shear stress was too high from these models. And so the K-omega SST model was proposed by Menter in 1994 in an attempt to address some of these problems and give better separation prediction for external aerodynamics applications. And that's the model we're going to look at today. So starting with the standard K-epsilon model, we've got transport equations for the turbulent kinetic energy K in equation 1 and a transport equation for the turbulence dissipation rate epsilon given there in equation 2. And at this stage, what we can do is look at the identity that epsilon is equal to c mu times by k and omega, and we can use this to compare the K-epsilon model with the K-omega model and see if we can identify any differences between the models that might be leading to the different observed behavior in the computations. And the way we're going to do this is by using that identity there, epsilon is equal to c mu k omega, and substitute that into the dissipation rate equation, and then compare that with the K-omega model to see if we can spot any differences. So if we substitute in, what we find is that we reach equation 3 there for the dissipation equation, and we can see that if we compare this with equation 4, which is the K-omega model, we can see that all the terms are the same. So we've got the temporal derivative, the convection term, then on the right hand side the diffusion term, the production and the dissipation terms are all the same if we compare equation 3, remember that's the K-epsilon model, just rewritten in terms of omega, with the K-omega model in equation 4. All of those terms are identical, with the exception of this additional term there in equation 3, which you can see with the underbrace. So this additional term appears in the K-epsilon model, but not in the K-omega model. And this might give us some clues as to what's happening and the difference between the models. So with this additional term, if we were to multiply the additional term, equation 5, by some function 1 minus f1, this would allow us to blend smoothly between the K-epsilon and the K-omega models. So that f1 there is just a blending function which can take any value between 0 and 1, and if our f1 has a value of 0, then that additional term exists as you see in equation 5, and the dissipation rate equation is the same as the K epsilon model. However, if we assign this blending function f1 a value of 1, then we can see that that additional term in equation 6 will disappear, it will be equal to 0, and our dissipation rate equation will reduce back to the standard K omega model. So this blending treatment is really a practical engineering treatment that we can use to blend smoothly between the K epsilon model and the K omega model. And what we would want to do really is we'd want to use the K omega model near the wall, as we don't have to use any damping functions in the K omega model, and we get much better near wall behavior. And then far from the wall, our model would switch to the K epsilon model, which is not sensitive or less sensitive to those inlet conditions that you might apply for turbulence intensity and turbulence length scale. So this blending approach that we're seeing here is really a practical engineering approach that will just allow us to switch between models through this single term F1 there. And we're going to be looking at F1 in a bit more detail in these slides. So just to recap, what we've got here is we've got the two scalar transport equations. We've got equation 7, which is the scalar transport equation for the turbulent kinetic energy, and then we've got equation 8, which is the scalar transport equation for the specific turbulence dissipation rate. And we've got the additional term in there, equation 8, and we can use F1, this single value, to blend between the K epsilon and the K omega treatments depending on where we are in the mesh. And when we're thinking about this blending function F1, we need to think of it as an additional scalar field. So like temperature or like velocity or pressure, that function F1 takes a value in every cell in the mesh. So every cell in the mesh is going to have a different value of F1. And for those cells where F1 is equal to 1, we'll be solving the K omega equation, and where F1 is equal to 0, we'll be solving the K epsilon equations. And before we move on and look at actually what functional form we're going to take for F1, I've put a small side point there for this this additional term, the gradient of the turbulent kinetic energy with the two double dots with the gradient of the specific dissipation rate. And you sometimes see different notation used for this term. I definitely hadn't seen it before. So for those of you who are confused, this is the tensor inner product of the two gradient terms there. And what that will look like in equation 9 is you could also write it using Einstein's summation notation, or just write it out fully. And how it would look would be partial k over partial x multiplied by partial omega over partial x plus partial k over partial y, partial omega over partial y, and so on for the three terms. And of course this will evaluate to a scalar value because it's a scalar transport equation. So if you ever see different notation or anything used for that additional term, this is really what it means. So before proceeding, I've just put on the slide there a little diagram for you to help understand what this blending function F1 is doing. Now this is just a section of the mesh near the wall, and what we want with our F1 is we'd like our F1 to take a value of 1 for the cells that are really close to the wall, and they're highlighted in red there. And then for our cells far away from the wall, we'd like our F1 to take a value of 0. And with this treatment, we'll be solving the K omega model in those cells that are near the wall, and the K epsilon model in the cells that are far away from the wall. And of course, if we choose a smooth value for F1, so rather than a step function, perhaps some smooth algebraic function, then in those intermediate cells, we'll be using a blend of the K epsilon and the K omega models, which will be fine using the setup we've used. So what form is currently used for F1? Well, F1 is currently used in the form of a hyperbolic tangent. And really the reason for using this hyperbolic tangent function, you could use anything, is that it gives a smooth transition between the K omega and the K epsilon models. So whatever this argument might be into the hyperbolic tangent function, we can see that when it's very small, F1 will be 0, so we'll have our K epsilon model, and then as our whatever this argument increases, F1 will tend towards 1, which will give us the K omega model. So now all we have to do is carefully choose this argument for this hyperbolic tangent function, and we'll get a smooth blending between the k epsilon model and the k omega model. And intuitively at this stage we think that the argument to this function should depend on the distance to the wall, because really we want our cells to be that are close to the wall to give us the k omega model, and the cells that are far from the wall in the middle of the free stream flow to give us the k epsilon model. So intuitively we expect this arg1 to be somehow related to the distance to the wall. And it turns out this argument that's used for the hyperbolic tangent function takes quite a complicated form, and it's given there in equation 11. And as far as our understanding goes, we don't really need to dive into how each of these terms appear in the sort of min-max limiter that you've got there. We don't really need to understand where all these terms come from. But the main thing for our understanding that we want to appreciate is that arg1 depends on the distance to the closest wall, d. So I've highlighted d there in red for you, and you can see it there in the diagram, that each cell in the mesh will have a scalar value d assigned to it, which is the distance to the closest wall. And as you can imagine, you might have to come up with some kind of sensible algorithm for computing the distance to the nearest wall, because some cells may be close to one or more walls. So somehow the CFD code will compute ahead of time the distance to the closest wall. Then we can evaluate the argument, and as we see there, if d is small, that means we're close to the wall, so arg1 is going to be very large, and from the previous slide that means that f1 is going to tend towards 1, and we're going to get the k omega model when d is small. So we're reproducing the exact behavior that we want. And as a small side point for our CFD codes, if our mesh is a stationary mesh, then we can calculate this distance to the closest wall once, and we can do that before we start the computation. However, if we have some kind of sliding or moving mesh algorithm, we're going to have to evaluate the distance to the closest wall, d, each time the mesh position is updated. So again, it can add a bit more computational expense to our computations. And as a small side point, we should also note that f1, in addition to blending the equations together, also blends the empirical constants between the k omega model and the k epsilon model. And we do that just using a linear interpolation there given by equation 12. And what we do is you substitute in whatever constant that may be a, b, c, a beta, whatever constant it is you're blending, and the value for the k omega model there is just given by phi omega. That's what I'm using as a placeholder, and the constant that you'd use in the k epsilon model will be given by phi epsilon there. And we use that same blending function f1 to blend between the empirical constants, so we do get a true blending between the k epsilon and the k omega models. At this stage, all we've proposed is the k omega BST, or baseline stress transport model. However, we haven't fully proposed the k omega shear stress transport, or the k omega SST model. And the reason for this was, in the original paper, Menter noticed that at this stage the k omega BST model was still over predicting the wall shear stress. So even though we had that blending between the k epsilon and the k omega models, we were still over predicting the wall shear stress. And so to extend the BST model into the SST model, we introduce a viscosity limiter. And the viscosity limiter will look something like equation 13 there. So on the left you can see the original form, or the standard form for the turbulent dynamic viscosity there. It's rho k over omega. However, what we do is we want to limit this viscosity, so by reducing that viscosity when we're close to the wall, when the shear is high, that means that our wall shear stress is going to reduce faster, and we're more likely to get separation if we carefully calibrate this limiter. And what we see there, if we take a minute to look at equation 13, we've got that max limiter on the bottom, and equation 13 will reduce back to the original form if S and F2 are small. So we reduce back to the original viscosity, and that will be far away from the wall. We have our original turbulent viscosity. However, if the product of S and F2 is large, then our viscosity is going to be limited, it's going to be smaller than we would get with the original model. Now S is the magnitude of the shear strain there, and F2 is another blending function. So this is going to be very similar to the last blending function we used, and this one is denoted by F2 to make sure that we're clear that it's different to F1, which was the blending function that we used between the equations. And F2 is going to be empirically calibrated as we did with F1. So F2 again takes a hyperbolic tangent form so that we ensure that the transition between the original viscosity and the limited viscosity is smooth, and as we expect, this arg2 also depends on the distance to the nearest wall, D, and that's highlighted there in red. So as D reduces, we get closer to the wall, our argument increases, and therefore F2, our second blending function, also increases, so we're more likely to be limiting the dynamic viscosity. I should also point out here that D is not the wall normal distance, Y, which we currently use for wall functions and wall treatment. It's the distance to the closest wall, which will be calculated slightly differently if we have a wall that's not aligned perfectly with our cells. So after proposing the K-omega SST model, Menter and a succession of other authors have found that the K-omega SST model gives much better agreement with experiments for mildly separated flows, and this is particularly important for external aerodynamic applications where we may have a wing or an aerofoil, and the results in the solution are going to be quite sensitive around that separation point. So we really want to be predicting separation well if we want to know when our wing and our aerofoil are going to start stalling, and that will be very important for predicting the performance of the aircraft. So the K-omega SST model gives much better agreement for these flows, separation from a smooth surface, and this is primarily due to that viscosity limiter that we saw in the previous few slides. At this point, it's also worth noting that the K-omega SST model has undergone slight alterations and updates since it was proposed in 1994, and there are slight modifications to lots of the production terms and limiters as well, and really we need to take care to ensure that we know what version of the K-omega SST model the code that we're using actually uses. And a very useful resource you can use for this is the NASA Turbulence Modeling resource page, which keeps a record of all the different variations of the K-omega SST model, and by comparing that with the manual for your code, you should be able to quickly work out which version of the K-omega SST model you're using. And as always, I'll leave a link in the description to this video so you can go and check out that page. And finally, some useful references. We've got the NASA Turbulence Modeling resource page and the original paper by Menter. I'll also put a link in the description below to where you can find that paper. And another interesting paper as well by David Apsley and colleagues gives a very thorough comparison of the K-omega SST model, the K-omega, K-epsilon models, and other turbulence models for flow in an inclined diffuser. So this is a flow where we get a slight expansion, and then due to the adverse pressure gradient we're going to be getting separation off the wall of that diffuser. And Apsley and colleagues use this as an excellent validation case to really compare the different turbulence models, and you'll be able to see quite well from this example that actually the K-omega SST model does do a much better job than many of the other RANS turbulence models for modelling separation from a smooth surface. At this point, as always, I'd like to thank everyone for watching this video, and thank you for your continued support and comments in the comment section below. I really do appreciate your feedback and like hearing from you. And as always, if there are any videos you'd like me to do or any topics you really think would be good to cover, please just drop a comment in the comment section below, and I do always try to get to comments and address them as soon as possible. And also, I'd like to remind you guys that I've also set up a website with summary notes for all of the slides and videos I've been doing, and there's also a link in the description below for that as well, where you can find lots of information, and you can find the equations as well. If you don't want to be flicking through the video all the time, you can go straight to the equations. Thank you all for watching, and I'll see you next time.